Welcome to Lesson 15A, Equivalent Diameters for Non-Spheres. I kept promising that we would talk about equivalent diameters when you have non-spherical particles. So now I'm finally going to do it. The reason we're doing this is because all of our equations of motion are based on spherical particles. So rather than come up with new equations for different kinds of shapes, we just come up with some equivalent spherical diameter so that we can just use the same equations. This is very similar to what we do in fluid mechanics with pipe flows when we create a hydraulic diameter to replace the real diameter. Once you have a hydraulic diameter, you just pretend that's a round pipe and use all the same equations. So in similar fashion, suppose we have some particle that has some weird shape. It's not spherical. The actual density of the particle is rho p, and there's some characteristic length scale. You could use that as a simple equivalent diameter, but it's not going to work very well. What we want to do is transform this into a spherical particle. We'll call that an equivalent sphere, and it has some diameter dp equivalent. Well, it's not immediately obvious how we do that. In fact, there are three different common types of equivalent spherical diameters. Two of them are based on settling speed, and one of them is based on volume. I'll talk about all three of them. The first one is called aerodynamic equivalent diameter. And you could read the definition here. It's the diameter of a sphere of unit density. So remember, that means 1,000 kilogram per meter cubed. The actual density is up here is probably not unit density, but we pretend it is. So we set that as the particle density. So that would settle at the same measured terminal settling speed as the actual non-spherical particle at its actual density. So looking at our diagram, suppose we measure this VT of the actual particles, and we know the actual particle density can be non-unit density, but we create in our imagination a sphere that's falling at the same VT, but this sphere has a unit density. Here's the procedure. You measure the settling speed of the actual particle. So that would be VT. Number two, you use our equation for settling speed VT from our previous lesson, except use DAE. That's the notation here for aerodynamic equivalent diameter. Use DAE instead of DP, and use rho naught unit density instead of rho p. So we'll use these equations for that general equation that we have to iterate for settling speed, but we're going to use unit density, and then we still need the properties of the air, and we're going to use DAE here instead of DP, but otherwise the equation is the same. The procedure is identical. Cunningham, all that stuff is identical. And then step 3 is to solve for DAE. Well, the problem is, like we've seen before, this is implicit, so it's not as simple as it sounds. In this case, it's implicit because C, the Cunningham correction factor, is a function, as we know, of diameter. So in this case, it's a function of DAE, and DAE is the unknown. So again, we're in this kind of loop here where we need DAE to find C, and then we need C to get our VT, and we're going to have to iterate. And so our CD is also a function of DAE because CD is a function of Reynolds number, and Reynolds number is a function of DAE. Good observation, BJ. Let's add that here as well. I use the method of false position to iterate, and I'll show you that in Excel. Before I do any of these calculations, I just want to give the definitions. Okay, the next one is DSE, which is spherical equivalent diameter. That's the diameter of a sphere of actual particle density that would settle at the same measured terminal settling speed as the actual non-spherical particle of the same actual density. If you compare these two, you can see I copied and pasted. The only thing different is the density. Here we set the density to 1,000 kilogram per meter cubed unit density. Here we use the actual rho p of the particle. So the procedure is identical to above for DAE, except the notation's different. We use DSE instead of DAE. So DSE is our spherical equivalent diameter, and we use rho p instead of rho naught. In other words, we use the actual particle density. Just a little comment about why we might do this. The spherical equivalent diameter is appropriate when you have cyclones and things like that that depend very much on the density of the particle, whereas this aerodynamic equivalent diameter, sometimes there are equations or correlations that are based on water droplets. So then you might want to use this DAE. The equation is here. It's the same as what we had up here, except instead of rho naught, we now use rho p, and we call this DSE. Again, this is implicit. Again, you must iterate. Why? Cunningham correction factor is a function of DSE. So we have that same problem that we had before. And CD is a function of DSE as well. You are correct again, BJ. I use the method of false position just as I did in the previous case. The third one, I saved the simplest one for last. This is called volume equivalent diameter, DVE. It's the diameter of a sphere of the same volume as the actual particle. So the procedure, you count some sample of particles, n or little nt, that's the number of particles, and you weigh them, take their mass, so you have some total mass. Calculate MP, which is the average mass per particle. That would be M total divided by N or NT. Then we calculate VP, which is the average volume per particle, and that'll just be MP, mass per particle, over rho P. And we're using the actual density of the particle there. If you had some other way to measure particle volume, you could do that as well, but this is how it's usually done. For example, you can get a whole bunch of particles and immerse them in water and look at the displaced volume, assuming you don't have any air bubbles and stuff. And that can give you a volume of the particle in a different way. Now we use the equation for volume of a sphere, which I conveniently happen to have typed up here. So the volume of the particle is pi dVe cubed over 6. I'm using this volume equivalent diameter, DVE, as the diameter of my sphere, of course. And then we just solve for DVE. And this one's pretty trivial. You get DVE equals 6 VP, volume of the particle, over pi, and that whole thing to the 1/3 power. And the nice thing about this equivalent diameter is there's no iteration required. This is an explicit equation. So that's the easiest one. Now let's do an example. Particles of density, I give a density, and we're using equivalent spherical diameters. We're going to actually calculate all three. These are SATP conditions. That's not always the case, of course. So they measure the settling speed and find it to be 3.46 times 10 to the minus fourth meters per second. They also count the particles that fall during a period of time, and they weigh them. Result is we have a mass per number of particles. So I'll just identify these guys. This is VT. This would be our total mass, and this would be our number of particles that were measured. So we're going to calculate all three of these: aerodynamic, spherical, and volume equivalent diameter. I duplicated all the equations here. I did all my calculations in Excel. Iteration is required for the first two cases, not for the third one. Now, if you've never used the false position method, I would invite you to watch my YouTube video about the method. It's actually quite powerful, and I think you'll find it useful in your careers and in other courses as you go through. Anytime you have an implicit equation where you have to do some kind of iteration. In fact, you could use this to find VT from our previous lesson, but that technique I gave you is actually a little quicker and easier to set up. But false position method is very powerful. Here's my YouTube channel, false position method in Excel. Well, you could watch that on your own. I used Excel for all three equivalent diameter calculations. And here's some screenshots. Part A, this may be hard to read. I used rho P equal rho naught. There's the 1,000. And then I set up my false position method exactly the same way that I did in that YouTube video. These are the converged values of VT from far to the right, because as a kind of intermediate step, I have to do that iteration like I did in the previous lesson to calculate VT. So in this case, I'm guessing some aerodynamic equivalent diameter. This is my first guess. And then I also have a second guess. These can be anything reasonable. And the way this method works is from there on, I'm linearly interpolating between the two previous values. And you can see how quickly it converges. The way I have the equation set up, like I explained in that video, the goal is to get this f of x to be 0. And it starts out 0.0026, then it quickly gets smaller and smaller. It's 10 to the negative 6 by the fourth line there. And it very quickly goes to 0. In fact, you can get it to be machine 0. This is 10 to the negative 17th and then actually 0. And so you get your final answer. So this answer is DAE equal 3.35 microns. By the way, I copied this whole iteration scheme from the previous Excel spreadsheet where I'm guessing VT, finding Reynolds number CD and a new VT, and this continues to the right. For part B, I copied and pasted this entire set of calculations here and just changed the title. The only difference is I set rho equal rho p, the actual density, so I do that here. And I just copied and pasted everything from the previous set of calculations, and you could see it also converges very rapidly. My final answer, this is now called DSE, equivalent spherical diameter, 2.33 microns. Notice that's not the same as previous DAE because of the difference in density. Finally, the easiest one, this one's kind of trivial. Using those equations that I gave you, the mass of one particle on average is m total over n. Using the numbers here, 0.158 milligrams over 8.22 million particles, I get 1.922 times 10 to the minus 8th milligram. That's the mass of one particle. The volume of this one particle is then mp over rho. I use the actual density of the particle, one unity conversion factor there on the denominator. And this gives me 9.563 times 10 to the minus 18th meter cubed. 10 to the minus 18th is really tiny, but this is in meter cubed, so that is correct. And then I use my equation for dVE based on the volume of a sphere. Plug in my particle volume from here, divide by pi raised to the 1/3 power, and then get my units correct by 10 to the 6th microns per meter. And I get 2.63 microns. And again, all three are different. We have 2.63 for DVE, we had 2.33 for DSE, and we had 3.35 for DAE. Now I'm going to show you this in Excel. Again, I strongly recommend that you put this into your own software in Excel or whatever other software so that you can figure these things out without trying to do it by hand. There's a lot of iteration involved. So this is very similar to what I had in the previous lesson. I kind of copied and pasted all these constants in, and then I enter my temperature, pressure, density, particle density, VT, when we're doing the measured terminal settling velocity. So that's the value that I had given. You'll recognize the 2010 from the problem that I just solved. And this is at SATP. I showed you this as a screenshot, but just to show you what's going on here, this in yellow is my first guess. My second guess, I convert to meters. My f of x is my goal. Now, in this false position method, it's best to set your goal for f of x as 0. So it's easy to tell when you have converged. What is f of x? Well, I'm trying to find DAE. So if I click here, what I'm trying to do is get DC30. So what's DC30? Well, we have to go all the way across to DC. So it's this final VT that I'm calculating through all this iteration process, minus C24 in dollars. So that's this measured settling speed. So when these two are equal, f of x will be 0. And of course, it's not 0 at first because I just have these guesses. So I make two guesses, and then this is just a linear interpolation. You can see the equation up here. There's linear interpolation so that I can predict a new DAE based on these two guesses and the f of x's. I explain that in more detail in my tutorial video about false position method. But as you can see, then I just copy and paste this down like this. And these other rows, you can actually grab a whole bunch of these, and I went all the way across, but I'm only doing 4 columns here to fill those down. And you can see that it converges very rapidly. I went too many times, but that doesn't hurt in Excel. It's easy to go to a very small number. In fact, it actually reaches 0. So there's my 3.35. For part B, spherical equivalent diameter, I literally did this. I grabbed all these rows, copied them, pasted them again here, changed the wording and the A to B, and all I did was change this to be C21, which is the particle density that I had specified. The rest of it's identical. I can use the same or different guesses. I just want to show you that this is pretty insensitive to what you guess. So let's just do 2 different guesses. Notice the answer is 2.335. Let's guess 5 and 20. I still get the same answer. In fact, these don't even have to straddle the final answer. So we call it interpolation, but in this case, it's actually an extrapolation. Of course, if I would pick 2.3 and 2.4, it would converge very quickly, but I'd kind of have to know the answer beforehand. But I can pick some pretty wild numbers like 30 and 1, and it still works once you have this set up. And then finally, the volume equivalent diameter, that's just using that equation for volume, and you can program that fairly easily, and I get my 2.63. So that's how I do that in Excel. Again, make sure you can get my numbers for my example problem using Excel or whatever other software you want, and then you should have no trouble with your quizzes and homework. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.